In this video, we will discuss the convergence of our numerical methods. In other words, can I get as close as I want to the exact solution when I compute the numerical solution? First, let us define the local truncation error. So we have an initial value problem with an ODE, y prime of t equals f of t y of t, and an initial condition, y of t naught equals y naught. Now, we have a one-step method, which is given by z0 equals y0, and a recurrence relation, which, as we said earlier, is zn plus 1 equals ft, tn, zn plus 1, zn. So that's what we defined in the previous video. Now, we will define the local truncation error as y of tn plus 1 minus ft of tn, ytn plus 1, ytn. Now, why do we define epsilon n, this local truncation error, this way? Well, that is because the local truncation error will be the difference between a true solution at tn plus 1. True solution is therefore y of tn plus 1. In other words, that's not an approximation. That's really the exact value of our ODE, of the solution to the ODE at tn plus 1, the true value. And what would happen if I was to put the true value to the IVP, but at one step before, which is what would happen at tn and maybe tn plus 1, right? So what we're saying is I'm plugging in the exact solution and into my numerical scheme, and I see how this reacts. That will be the local truncation error. Of course, I do not know what is the value of y at tn or at tn plus 1. If I did, then there would be no point in trying to find it numerically, right? But what I'm saying is, if I was to know it, then I will call epsilon n that local truncation error. Let me give you an example here. If we have a one-step explicit method, so we have an increment function phi, we have epsilon n, that will be y of tn plus 1 minus, well, obviously ytn, it's minus with parentheses, so basically I distribute my minus sign, minus h, my ht, my step, and my increment function of phi tn ht y of tn. Let us now define the consistency. A numerical method will be called consistent if, when I sum the local truncation errors from 0 to n minus 1, then the limit will go to 0 as the step goes to 0. And by the way, if on top of going to 0, I can actually characterize how fast it goes to 0. In other words, if it's in the Landau notations, ht raised to power p plus 1, then that means that we'll say that the consistency is of order p. Okay, so what does this mean? It means that obviously we have truncation errors, local truncation errors at each step, and obviously they will add up. Now, the consistency means that we can render the sum of these local truncation errors as small as we want, provided that the step h is small enough. So you see, when the step goes to 0, what it should do is to get our local truncation error really going to 0 if we want to have a numerical scheme, a numerical method that is consistent. And as you see, it has to not only go to 0, I mean, the truncation error, local truncation error has to go to 0, but it has to go to 0 fast enough to compensate for the fact that you have more and more local truncation errors that will add up. Okay, so let me show you what it means on the graph. So here, this is for instance, the Euler forward method. I start at t0, y0, and then I go in the direction of the tangent. I go a delta t, or ht if you prefer, or h if you prefer. And what happens is I get here I'm not exactly in the solution, right? I am slightly below in this case. I could be slightly above. Here I'm slightly below. And what happens is that I'm not in the red curves, which is the exact solution. I'm slightly off. Now, the difference between where I am and where I should be is this epsilon 0, and epsilon 0 is the local truncation error. Now, for consistency, means that the sum of all of these small, very small orange segments will be, when I sum their length, that will go to 0. So, and again, what it means is that the number of such lines will go up also. I mean, if you reduce ht, well, obviously, what's going to happen is to get from 0 to 0.5, you're going to need more steps. So you're going to have more lines, orange lines that will add up. So what you need is these orange lines to go to 0 faster than the number of lines that basically are adding up to and obviously making the error to accumulate. So that is what consistency means. Let me give you an example here. If we consider the Euler forward method. Now, what happens is that we can actually compute the local truncation error, right? Because we can say that ytn plus 1 equals ytn plus h, ftn ytn plus oh square, right? So when I have this, and which this comes simply from the Taylor expansion, right? I mean, it's just like nothing more than the Taylor expansion, where I know that I can replace the y prime by ftny, by fty, right? This is just because it's an ODE. So because I have this, I can actually get two terms on the left-hand side, and what I obtain is this. I'm saying epsilon n is O of ht square. Now, when I add up this epsilon n, and again, epsilon n, it's not epsilon raised to power n. It's a superscript. It's a superscript. It's just an index, if you prefer. So when I add up these epsilon n's, well, what I will basically do is add up this O of ht square. How many do I have? N. N is really t over ht. So what we have there is O of ht, which means that the limit is 0. And on top of this, I can say that the Euler forward method is going to be of order 1. So it is consistent since the limit is 0, and it's of order 1 since it is h raised to its O of h raised to power 1. So the Euler forward method is consistent. Now, a necessary and sufficient condition for consistency is simply that phi, basically phi is consistent. The method is consistent if and only if we have phi t 0x equals f of tx. And you can just go back into the equation, the previous equation, do exactly what we did for the Euler forward method, and see that this actually will do the same thing and will have consistency. Now, we talked about consistency. We're going to talk about something different called stability. What is stability? Well, let's eta n be a perturbing sequence. So we have z0, we have y0, and then we're going to have zn plus 1, which is basically the k-step method here with k equal 1. So it's a one-step method to compute each term. So basically we have a numerical method. And then we're going to have a wn, which does the same thing, but at each term we're basically going to perturb the sequence a little bit. So you can think of as eta as numerical error or something else, or adding up local truncation error or something. Something is perturbing my sequence wn. Now, the numerical method will be stable if Zn minus Wn can be bounded by a constant times first Z0 minus W0, I mean the distance between Z0 and W0 when we started the numerical scheme, plus the sum of the norms of the perturbations. Okay, so what we're saying is stability means the method will not amplify the small perturbations eta n. They will be there, obviously. I mean, you know, we cannot do much better than that. We have perturbations that we don't know, but what we don't want to do is amplify the errors, amplify the perturbations with the numerical scheme. If we don't amplify these errors, if we don't amplify these perturbations, then the method will be called stable. For a one-step explicit method, I can rewrite this using my increment function phi. And here's what I get, simply. And what I would like to show you is, in this case, okay, what happens if I write Zn plus 1, Wn plus 1 with basically my function with an increment function, which will be the increment function coming from the Euler forward method. Well, in this case, I just write Zn plus 1 and Wn plus 1. I do the difference, and what I obtain, obviously, is Zn minus Wn plus Ht, f of Tn Zn minus f of Tn Wn. And of course, I have my perturbation, eta n. Now, I can put this in this form, and you see that what we see here is that the norm of Zn plus 1 minus Wn plus 1 will be bounded by the norm of Zn minus Wn plus the step and the norm of Ftn Zn minus Ftn Wn plus, of course, the norm of my perturbation. But now, if my function f is Lipschitz continuous with respect to the second variable, then it means I can actually bound my norm of the difference of the functions by that Lipschitz constant times the norm of Zn minus Wn. In other words, when I put all of this together, I end up with 1 plus HTL times the norm of Zn minus Wn plus the norm of the perturbation at step n. And since obviously I'm going to have to kind of iterate this, then I would like to point out that 1 plus HTL will be smaller than exponential HTL. Now I can use a lemma, which is a lemma that you will prove in the problem set, and which is somehow related to Grunwald's inequality, but that's the discrete version. Well, what we're saying is that if we have two sequences, alpha n and beta n, that are non-negative sequences, and if Q is in R plus, and we have alpha n plus 1 smaller than Q times alpha n plus beta n, and again, these are superscripts, they're not powers, then what we'll end up with is alpha n smaller than Qn alpha 0 plus the sum of Qn minus 1 minus n beta n for n between 0 and n minus 1. So in a sense, it's the generalization of what we know for geometric sequences. If we have a geometric sequence, alpha n plus 1 smaller than Qn alpha n, in other words, the beta is equal to 0, then obviously we'd have the first part, with the beta in the mix here. Here's what we get. Okay, so here what we're going to do, of course, is use this lemma with alpha n equals Zn minus Wn, norm of Zn minus Wn, and beta n, the norm of the perturbation. And Q will be the exponential of HTL, and you see why I prefer this exponential of HTL rather than the 1 plus HTL, is because when I raise this to power n, then it will be really easy to see what it is. So Zn minus Wn will be smaller than this exponential, well, obviously NHTL, multiplied by Z0 minus W0 plus the sum of this exponential with this eta n. So let me actually rewrite this this way. Since n times ht is capital T, then here is what I obtain. Here's the result. Okay, so let me actually put this in this form. It's actually consistent, no pun intended, with the definition we gave. So obviously, what we just proved is that the one-step method is stable provided that phi is Lipschitz continuous on its second variable. And obviously, as I said, that means that for the Euler forward method, that will give us the, we'll have stability. However, there is a bad news. The bad news is that exponential LT means that if we have a very large t, somehow we're bound by something which can be potentially quite large. So that is not a great news. Well, if we had not replaced exponential, 1 plus ht L by exponential LT would still somehow have the same problem, which is that this expression here, when t is large, can get pretty large. Okay, so we have discussed stability, and before that we had discussed consistency. What we're really interested in knowing is whether the numerical method is convergent or not. And convergence means that the numerical method is going to be convergent if the maximum error, what we called En, previously, if this En goes to 0. That's what we want. In the end, forget about consistency, forget about truncation errors, stability, forget about all of this. What we really want is to have this, convergence. Okay, well, the reason why we discussed consistency and stability is because obviously, not obviously, but we'll see, it's not obvious yet, that this is going to be linked to the convergence. And actually, again, what does convergence mean? It means that the solution approaches the exact solution to the PDE and converges as the step tends to 0. And this will be exactly linked to what we had before, which was consistency and stability, thanks to the Lax equivalence theorem, which says that a consistent numerical scheme for which the initial value problem is well posed will be convergent if and only if it is stable. So you see, when you have consistency and stability, you will have convergence. And of course, since the Euler forward method is both consistent and stable, then the Lax equivalence theorem will tell us that it is convergent. All right? So let us see why this theorem, how we prove this theorem. Okay, so we have defined the local truncation error earlier. We have defined also En as y of Tn minus Zn. So you see there is a difference between epsilon n and En. Now I'm talking about En. En is the difference, not between y of Tn plus 1 and what would happen if I was plugging in the exact solution in the scheme. No, I'm really talking about what is the exact solution, y of Tn, and what I find with my numerical method. So that is En, not epsilon. And E capital N, as we said before, is the max of the En between 0 and n. So what we will want to prove is that, provided of course that we have stability and consistency, that the limit of capital En, the maximum error, will go to 0 as the step h goes to 0. And in terms of order, we want to prove that En will be, with the Lambda notation, ht raised to power p. Okay, so we will call m a parameter, and we'll define a sequence capital Z and m for n greater than m by y of Tm if n is equal to m, and the ft Tn minus 1 Z and m Zn minus 1 m if n is greater than m. So I just would like to emphasize that m is a parameter and the index of the sequence is the superscript n. Okay? All right, so we have therefore Zn, which is small zn, which is capital Zn 0. Okay? Now, let's go back to our error, to our y of tn minus zn, or en. What we'll have is that this is simply capital Znn minus capital Z0n. Okay? Now, I can, of course, add Zn minus 1 and subtract Zn minus 1 and go all the way to Z0. And if I do this, then, then what I will get is simply that the norm of En will be bounded by the norm of Znn minus Znn minus 1 plus the norm of etc., all the way to the norm of Zn1 minus Zn0. Therefore, let me write this way. That's the sum, that's bounded by the sum for k equals 1 to n of zkn minus zk minus 1n. But we know that znk and znk minus 1 both satisfy the same recurrence relation. They just differ on their initialization, right? So now what we're going to do is to use the stability of the numerical method. The stability of the numerical method says that znk minus 1 is bounded above by k times y of tk minus ft tk zk k minus 1 y tk minus 1. And then what we say is, okay, but the consistency of the numerical method will yield that znk minus 1 is bounded by this k times that norm, but that norm is itself bounded because, of course, of the consistency of the numerical method. So we end up with znk minus 1 to be bounded by k prime h prime p plus 1. Subsequently, what we'll have is that En is bounded, the norm of En is bounded by k seconds, a different constant, doesn't matter, h p, and h, basically write it ht or h, I mean that's the step raised to power p. So what we end up with is that this maximal error is bounded by another constant, that doesn't matter, times h raised to power p. Well, which means that, En goes to 0 as h goes to 0, which proves the lax equivalence theorem. All right, we still have a question to address, which is what happens when capital T is large? And we have investigated the solution on 0t. We know we have convergence. But if we choose a large t, what happens? And we already have a hint, which is that things might not be so great, because when t is large, my exponential lt, which is my bound, is large as well. Now, just because the bound is large doesn't mean that things go astray. It just means that we don't really control things, right? So maybe things go well, maybe they don't. So let's just look at this equation, which is called Dahlquist equation. Very, very simple equation. It's the one we talked about in the introduction. Y prime of t equals lambda y of t with the initial condition y of t naught equal y naught. Okay. So let's say, for instance, I choose lambda equals -10. So lambda equals -10 is known to provide a solution which is going to be y naught times exponential -10t. So if y naught is 1, then the solution will simply be exponential -10t. And we know that this is perfectly stable in terms of, in terms of initial condition. If I start close to 0, then I will have my solution going to 0. So it's not an ugly equation. It's actually a pretty simple, pretty nice equation. Things are going well. Now, let's try to apply the Euler forward method to it. So let's start with z0 equals 1, and I'm going to do zn plus 1 equals zn plus ht lambda zn. Okay? So what we have is Zn equals, well, 1 plus lambda ht raised to power n. So far, I mean, it makes perfectly good sense, right? And we have h, which is -10. So what it means is that we have Zn equals 1 minus 10 ht raised to power n. This will diverge if the step is not very small. If the step is greater than 1/5, then the Euler for one method will not converge, because obviously I raised to the power n something that is not in absolute value smaller than 1. So my Euler for one method will obviously work. I mean, we proved convergence, so it's going to be a convergent method. However, what we're saying is that we have a pretty strong basically requirement on the HT, which is that it better not be too large, otherwise things will not work. Okay, so you need a very small step. Which means that if you want to approximate your solution on a very large 0 capital T, you may end up with, well, it may take some time to do that, and you're going to have to control this error pretty well, because obviously, error might, so it's a problem. So it's a problem. Okay, so let me define astability. The astability is, for a method, it is if the limit of Zn equals 0 when the method is applied with a fixed positive h to any Dahlquist test equation. Okay, so we're not talking here about the stability of the equilibrium. And let's not confuse the stability of the equilibrium and stability of the method. Here we're talking about the stability of the method. The stability of the method, we have astable if when you apply it to the Dahlquist equation with lambda with a real part which is negative, then when for any fixed positive h, then you have limit of Zn equals 0. So obviously the Euler for one method is not astable, and that will actually well, lead the way to actually discussing a few other methods, and that's exactly what we're going to do in the next video.